Hey, welcome back to Math with Patrick. It's March 22nd, and we have the 81st problem from this Daily Epsilon calendar to solve. And of course, the answer is 22. That's today's date. So the variable y is equal to this sum. We're going to have 21 different summands or terms in our sum, and they're each going to be a product between n and n factorial. Eventually, once we figure out what this sum is, we could plug it in here, add a 1, and that's supposed to be the same as 22 factorial, because again, x is going to be what we're solving for, and today's date is the 22nd. So I'm already a little bit worried here, because, just definition of factorials, that is just defined as all of the natural numbers below, or including and below your current number, all multiplied together. And so that's going to be 22 times 21 times 19 times 18 times 17, all the way down to times 2 and times 1. This is going to be an obnoxiously big number. Like, I don't want to do all this multiplication, and I'm a little worried because apparently y is going to be 1 less than 22 factorial. So it'll be a little tough to figure out what that number is because it's just so big. Let's see what happens if we try to evaluate the sum, just kind of like brute forcing it. So the way to read this notation is that you set n to be equal to 1, or whatever this bottom number is, plug it in here, and then write whatever you get, and then you're going to add the same thing, except this time n is going to be equal to 2. And then you add the same thing, but this time n is going to be equal to 3, and so on, all the way until you reach the final term, which is when n is going to be equal to 21. So plugging in 1, I get 1 times 1 factorial. I guess I'll just write it all out. 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus all of those all the way up until 21 times 21 factorial. Now this first term is just 1 times 1, so that's 1. This next term is 2 times 1, which is 4, so not that bad. The next one is 3 times 2 times 1. So that's 3 times 6, or 18. And then eventually we're going to get this large number. And this one is just going to be so big, I can't compute it. At least not in my head, and I really don't want to do it on paper. And maybe some calculators can't even fit this number in their system. So at least just brute forcing it doesn't really seem to work. Because then I'd need to finally add 1, because this number right here is y. And I'd add 1, and then I need to somehow backtrack and figure out that 22 factorial is this number. And that just feels really hard. So here is a math trick that I can show you. Instead of dealing with really large numbers and really large sums, you might be better off finding a pattern with smaller numbers and smaller sums. So let's investigate. Here, I'll write this down. Let's investigate. Instead of the sum from 1 to 21, let's just think the sum from 1 to, n, how about? As in, capital N being maybe it's 1, maybe it's 2, maybe it's 3. And then here, let me just rewrite the n times n factorial. So if I create a little table here where big N is going to be the amount of terms in my sum, and I'll just do sum over here. So when n is 1, I just have this first term, so it's just 1. When n is 2, I get the second one, so I get a 5. And then 5 plus 18 is 23. And maybe it would be useful to get the next term in this sequence. So when n is 4, let's see, I'm going to add on a 4 times 4 factorial. That's 4 times 24, and that's going to be 96. So 96 plus the 23 is going to get me to 119. And I'm noticing a pattern here, just because if I add 1 to all of these values, so if I do sum plus 1, I got 2, 6, 24, 120, and these are actually our factorial numbers. This is 2 times 1. This is 3 times 2 times 1. This is 4 times 3 times 2 times 1. And then finally, 120 is the same as 5 times 4 times 3 times 2 times 1. So it seems like it doesn't really matter what this top number is. I'm always going to have this pattern. So like it already kind of makes sense to me why if the 21 is here, we're going to get a 22 here. Kind of like how if there is a 4 here on the top of my sum, I'm going to get a 5 factorial as like that answer to the problem. So I tried solving it just kind of straight up, straightforward, too hard. I'm getting this pattern, and now I want to prove that this is going to be true for all cases. Because even though we see that 4 entries follow this pattern, maybe if I do a 5 here, I'm not going to get a 5 factorial over here, or like 5 factorial minus 1 here. Maybe the pattern breaks. So induction is going to be the tool that I use here. I've used this tool in a previous video. Essentially, you need to claim that you have some kind of base case or a starting value is true. And then you need to prove that if a given step is true, then the next one is. And with those two claims that a step is true and if a step is true, the next one is true, well, then you can just keep on incrementing up and up and up and prove that all different values of that capital N are going to be true. So Quill has joined us for our use of induction. And fortunately, any of these that I've already written in this table could be my base case. Because I know that this is true for various different small values of this big capital N. And I don't need to show any more for induction. Now I need to show that inductive step. So we're going to assume that some step is true. We're going to assume that the sum from n equals 1 to k of n times n factorial is going to be equal to, let's see, it'll be k plus 1 factorial minus 1. Because again, this k, you could think of it maybe as the 4. And we notice that after just trying out the numbers, this sum will equal 5 factorial minus 1. That's the 120 minus the 1. And so over here, that's why I did k plus 1 in parentheses, because I wanted this to be basically the 5 over here. Then I hit it with the factorial, and I'm subtracting 1 because that's just the pattern that I see to go from this number to that number. So in induction, we just assume that this is a true step, and we want to show that the next step is true based on this previous information. So I really want to show that the sum from 1 to k plus 1 of n times n factorial is equal to, oh wait, hold on. This should be a k plus 1, right? Okay. It should be equal to k plus 2 factorial minus 1. All right, how do we do this? Okay, let's break up this sum right here. So it's going to be the sum from n equals 1 to k, so the first k terms, and then I could just write the last term itself. That will be when I plug in a k plus 1 here, and then a k plus 1 factorial over here. So all I did was just kind of break up the sum notation, and I have k plus 1 different things all added up. So the first k, or basically all but 1, are going to be in that sum, and the very, very last one is right here. And again, I want to show that it's equal to this. What will I do? Well, I guess I can assume from my previous step that this first sum of all those k terms is just going to be equal to that k plus 1 factorial minus 1. So this part changes to there. And let's just keep that k plus 1 times k plus 1 factorial just the way it is. Now I want to change it so it looks like this. I already have this minus 1 here. So I guess let me stick that -1 at the end, because that's where it is here. This -1 is already at the end. So k plus 1 factorial plus k plus 1 times k plus 1 factorial minus 1. I'll just draw an arrow here to say all I'm doing is scooching this -1 at the end. And let's factor. I see that I have two terms here and here, and they both have a shared factor of k plus 1 factorial. So I can factor out a k plus 1 factorial. And let's see what's left behind. There's nothing left behind here. I basically factored out the whole thing. So a 1 is the most appropriate number to put here. You can imagine redistributing it, and then k plus 1 factorial times the 1 gets you back here. And the thing that's left over from the second term is a k plus 1. There we go. And the -1 is still hanging out. And if you notice, this right here is k plus 1 plus 1, or k plus 2. So just to be super, super clear, I'm going to write that out like that. Again, -1, still hanging out. And then this is just the definition of k plus 2 factorial. It's k plus 2 times k plus 1 times k minus 1, and all the numbers all the way down to 1. So I can rewrite this as k plus 2 factorial minus 1, which is what I wanted to prove all along. There it is. So if I can assume that my previous step is true, I now know that the next one is true no matter what. So I'll just do a little arrow up here to say, haha, I got it. They match. So I think this basically just proves it, where now I know that for any value of k over here, I'm going to get k plus 1 factorial minus 1. And so if I add 1 to that, I'm going to get k plus 1 factorial. I don't need the parentheses anymore. K plus 1 factorial. Well, maybe I do, because then it looks like 1 factorial plus k. So I'll keep the parentheses there, just to be super clear. So it doesn't matter what k I put. Just by happenstance, what if I put 21? That's the number that was there in the original problem. I put a 21 there, then I'm going to get 22 factorial minus 1. And if I add a 1 to it, which is exactly what's happening here, then I'm going to get just 22 factorial. And it's that number right here. It's this 22 that we wanted to match to today's date. And because it matches, and because it's proven through induction, we're done. So I didn't even figure out what y was. I don't even know how big that number is going to be. However, I am completely certain that if I add 1 to y, I'm going to get 22 factorial, and 22 is today's date. So I'm all done. This is the problem. And thanks for figuring this out with me. So here's another shot of Quill, just as a thank you for coming along for this whole trip. And I'll see you in the next episode tomorrow. All right, bye.